Good morning, everyone. This is Arnav from PyCode. Today, we'll be doing chapter number 2 Encoding Schemes in Number Systems. So, what is a number system? It is a set of values used to represent different quantities. For example, a number system can be used to represent the number of students in a class. The digital computer represents all kinds of data in form of binary numbers. The total number of digits in a number system are called its base. The base is written after the number as subscript. So 512 to the base 10. What are the different types of number systems? There are four types of number systems that we will look at today. These are the binary number systems, octal number systems, decimal number systems, and hexadecimal number systems. Now, this is an extremely important table which I would request to everyone to memorize. Now, it might seem daunting at first, but there's a really short trick how which you can memorize this. So, we write all the decimal numbers from 0 to 20 on one corner. Next, for the binary number system, we start with 0, then 1, then 0, sorry, we start with 0, 1, 0, 1, 0, 1, and so on until we reach 20 where there's a 0. Now, if you closely look, the second number from the right side starts with a 0. So two zeros, two ones, two zeros, two ones, two zeros, two ones. Similarly, when we go through to the third digit from the right hand side, we see there are four zeros, then four ones, one, two, three, four, then four zeros, then four ones. And then when we go to the fourth digit from the right side, we see that there are eight zeros, and then there are eight ones. So this is exactly how we write down and memorize for the binary number system. Now for the octal number system, we write the numbers. It's the same from 0 to 7, but after 7 we skip and move directly to 10, and then we once again write the numbers till 17 and then directly skip to 20. Now, all you have to remember is that from 7, the next number is 10, and from 17, the next number is 20. Rest, it remains the same as the decimal number system. It's pretty much the same for hexadecimal as well. Apart from that, after we move on from 9, 10 is represented as A, 11 B, 12 C, 13 is D, and this moves on till 15, which is F. So they're from A to F, and then we once again start with 10, 11, 12, 13, 14. So this is an easy and short way you can memorize this table. And I would recommend that you guys go through this table, and in your examinations you can actually draw this table in the rough column. This would be extremely helpful for solving such problems. So the binary number system uses numeric base values as 2, and it has two unique digits called 0 and 1. So it is the language of the computers. Everything we type, inputs, outputs, all of them are in binary language. A single binary 1 or a single binary 0 is called a bit, which is short for a binary digit. Now 4 bits of a binary number make a nibble, and 8 bits make up a byte. As you can see, there are 4 digits here, so there are 4 bits here. This is a nibble. There are 8 bits here, so this is a byte. Now we come to the most important section, which is the conversion from decimal to binary number system. So let's say we're given the number 65, which is in base 10, or for decimal it's also called base 10. Remember that. And binary is base 2. So from base 10 to convert to base 2, we divide the number by the base. We divide the number by the base which we want to convert it to. So over here we want to convert it to binary. So we divide the number by 2. Now, on the right hand side, we make a column called the remainder section. and every time we see that the number is not completely divisible, we add the remainder as 1. So when we divide 65 by 2, we get 32 as the quotient and 1 as the remainder. So we place 1 in the remainders column. Then we divide 2 with 32 and we get the quotient as 16. Now, since there is no remainder, we put 0 on the right hand column. Once again, 16 divided by 2 is 18, 0. 8 divided by 2 is 4, 0. 4 divided by 2 is 2, 0. And 2 divided by 2 is 1. We once again place 0. Now, after reaching here, we know we what we do is we take the number which is in the quotients column, this column, and it is this second last number. So let's say after here we see that there is no more number which can be divided by 2, since 1 the quotient is smaller than 2. So what we do is we put 0 in the quotient and we place this number which is 1 in the remainder section. So this comes right here, and when we write down the number, it goes in the reverse order. So as you can see, the arrow goes from down to up, so that's how you calculate. So this becomes, the number then becomes 10000001 in binary or base 2. So that is how we convert from decimal to binary. I would like to once again say that try doing this problem on your own, and after my explanation, and go back and play the video once more to get a greater clarity of the understanding of the concept being applied here. Now from decimal to octal, once again, as I mentioned earlier, the base in which we want to convert to, we write that to be divided to. So we divide it by octal is base 8. So we divide it by 8, the number by 8. Now 8 8s are 64 and we get the remainder as 1, as 65 minus 64 is 1. Then 8 divided by 8 is 1. Hence the remainder is 0, since there is no remainder. Then as I mentioned, we place the second last digit. We first put 0 below 1 and we place this digit right here, and then we count the number in reverse order. So this becomes 101. Hence here's the answer. Now to convert from other number systems to decimal, there's this rule which you should always follow. Step 1 is writing the position number for each alphanumeric symbol in the given number. Then writing the positional value for each number system by raising its position number to the base value. Then multiplying each digit with the respective positional value to get a decimal value. And then adding all these decimal values to get the equivalent decimal number. Now let me break this down for you. Let's say we're given a number 1101 to the base 2 and we want to convert it to base 10 or the decimal number. What we will do is we take the given base and we multiply it through powers. Let me explain. So the given base is 2, right? And the first number. So for these type of questions, before the decimal place, we move from right to left, and after the decimal place, we move from from left to right. So over here, 2 to the power 0 times 1 plus 0 into 2 to the power 1 plus 1 into 2 to the power 2 plus 1 into 2 to the power 3. That is how we solve the problem. So the first number is taken 0. 1 will be taken as 2 to the power 0. Then for 0 we will take it as 2 to the power 1. Then the next one will be taken as 2 to the power 2 and this as 2 to the power 3. And we will multiply these given numbers by 2 to the powers. So as you can see, 1 times 2 to the power 3, 1 times 2 to the power 2, 0 times 2 to the power 1, 1 times 2 to the power 0. This gives us the answer as 13. Now, if we want to convert 257 into decimals, Once again, we check what the given base is. Now the given base is 8. So what we do is that the first number is taken as the base to the power 0. So 7 into 8 to the power 0. Next is 5. So 5 into 8 to the power 1, and then 2 into 8 to the power 2. And all of these numbers are actually added up to give the final answer as 175 to the base 10. Now, if you recall from the previous table I had shown earlier, A is actually 10. So, what we do is the given base is 16 and we want to convert it to decimal. So 16 into 5 to the power 0 right here, plus 16 into 10, since A is also 10, then 16 square times 3, which is given here. We add all of these up and we get the sum as 933. To convert to binary to octa or hexa and vice versa, what we do is group them. So we want to convert the number into octa. So this is an important point to note. Please note this somewhere, that whenever we want to convert the number to octa, we group by 3, and whenever we want to convert to hexa, which is also 16 bits, we group them by 4. So as I mentioned, we group for octa 3s, right? So we move from right to left and we group them by 3. So this becomes 001. I wrote that here. Then 101. I write that here. Next, we have 01. That is only two numbers. So what we do is that to get the third number, we just put a 0 before that, because 10 and 010 is the same. So that gives us three numbers grouping. Now we go back to the table and check. So let's say we have 010. So for 010, we can see that the decimal number is actually 2. So we write 2. Similarly, 101 is 5 and 100 is 4. So the number becomes 254. For hexa, we group them in fours, in pairs of fours. So one pair will be 0011, second pair is 0101, and the last pair becomes 10. But since we want to pair them in fours, we add two zeros because 1 and 0001 are the same. After this, we write the hexadecimal symbols for each group. You can refer back to the table and see that 1100 is C, 1010 is A, 0001 is 1. So for the hexadecimal number, this becomes 1AC to the base 16. Now if this is the opposite and we want to convert it to binary, we take the octa digit numbers and we write their equivalent 3 bits binary digit numbers, since we're converting from octa to binary. So we can refer back to the table and again see that this is 101, this is 000, and this is 111. I would recommend that all of you actually make the table first in your notebooks and then watch the entire video to get a better clarity of how the steps are taking place. To convert 23D to the base 16 to binary, we group them by 4 by writing 4-bit binary values for each of these digits. And once again, you can refer back to the table. D is 1101, 3 is 0011, 2 is 0010. So the number in binary becomes this. Now let's say we want to convert them with fractions. So what we will do is, we see that the base which we want to convert is binary, which is base 2. So we will multiply the number which is in the form of a fraction or decimal with the base which we want to convert it to. So that is 2 in this case. So we multiply it by 2. And what we do is, on the right hand side, we write the values after multiplication. So it becomes 1.35. Now what we do after this is we make another column and we write down the integer part. What I mean by integer part here is the value before the decimal place. So all these values. So 1, 0, 1, 0, 1, 1, 0. We write these down in the integer part place. And let's say we got 1.35 here. Now what we will do is we will ignore this one part and we will take the 0.35 part and then once again multiply it by 2. And whenever we get a number which is in 1 point something, let's say 1.2, 1.3, 1.4, 1.5, it really doesn't matter. We ignore the one part and multiply the number by zero point 0.4 times 2. And then this process goes on. You can actually repeat this process as many times as you want. So this can be repeated 3 times, 4 times. I would say for a rule of thumb, you do this multiplication process at least 4 times to get the answer. And the final answer then becomes, we go from top to bottom in this as the arrow shows. This becomes 1010110. Now if we want to convert 0.675 to the base 10 to octal, which is 8, we multiply it by 8 because that is the base which we want to convert it to. So that gives us 5.4. Now we take the integer part, this one, and write it down right here. So for this one, 5 is the integer part. Then we take, after the decimal place, we take the number and multiply it once again by 8. Now we get 3.2. So 3 is the integer part, we write it here. Now 0.2, we multiply with 8, we get 1.6. We write down 1 here because that is the integer part. Then we take 0.6 and then multiply it by 8. Then we get the answer as 4.8. We write 4 as the integer part and 0.8 is once again multiplied by 8 to give us 6.4. So then the answer becomes 53146. Similarly for hexa, we multiply it by 16 and over here the integer part is 10 and 12 respectively. So 10 is A for in hexadecimal and 12 is C. So this becomes AC. Let's say we want to convert from base 2 to base 10 or from binary to decimal. What we do is pretty similar to what I explained earlier. Just that we are adding decimals right here. So as I showed earlier in the PPT, first is 2 to the power 0, next is 2 to the power 1, 2 to the power 2, and so on. So first number before the decimal place right here is always taken as 2 to the power 0. And all of these numbers are multiplied with each other and their sum actually gives us the decimal value. But once we come after the decimal place, right here, we don't multiply by 2 to the power 0. Instead, we start multiplying by 2 to the power negative 1, which is taken as for the first number. Similarly, when we move on 2 to the power negative 2, then 2 to the power negative 3, then it moves to 2 to the power negative 4, then it moves to 2 to the power negative 5. Now, we add all these separately, the ones before the decimal place and after the decimal place. This gives us 37 before the decimal place and 0.625 after. Now we add both of these and this gives us 37.625. Similarly, for converting from base 8 to decimal, we write down with 8 to the powers. So over here, once again, after the decimal place, since it's after the decimal place, we take 8 to the power negative 1 and the second one is 8 to the power negative 2. And we add both of these separately and we get the answer as 1029.15625. To convert 10101100.01011 to octal, as I mentioned earlier, we make perfect groups of 3 bits each. So after the decimal place, you will see that we move from left to right. But before the decimal place, we move from right to left like this. So that is how the grouping is done. So for before the decimal place, for 3 digits, we take 0, 0, 1. We write that here. Then 1, 0, 1. We write that here. Next, we have 0, 1. but we want 3 bits, right? So we add 0 before that. And after the decimal place, we move from left to right. Remember this, that we always move from left to right after the decimal place. Note this down. So for 3 bits, 0, 1, 0. Then we write this down. Then 1, 1 we're given, but we want to make perfect groups of 3 bits each, right? So we add 0 after 1, 1. Then we write the octal symbols using the table which I had shown earlier. And then we just simply write down the answer. Now this is an important point to note, that make 3-bit groups from right to left for the integer part, which is this one before the decimal place, and left to right for the fractional part, which is after the decimal place. Now similarly, to convert from base 2 to base 16 or the hexadecimal one, we make groups of 4 bits each. So this becomes 0, 0, 1, 1 right here, and 0, 1, 0, 1 right here. Then after the decimal place, we look from left to right. So 0, 1, 0, 1. Then we have 1, 1. But we want to make a perfect group of 4 bits. So we add 2 zeros after that. Then we write the hexadecimal symbols using the table. So this is equivalent to A, this is C, this is 5, and this is C. So answer becomes AC.5C, which is in base 16 or in the hexadecimal form. Now, if we want to convert a hexadecimal number to octa or vice versa, what we do is we first convert the hexa number to binary, then we convert the binary number to octa, or we convert the octa number to binary, then we convert the binary number to hexa. So 5 is same as 0101 in binary, 2 is same as this in binary, 8 is same as this in binary, D is same as this in binary, 3 is same as this in binary. Now, since we want to convert it to octa, and I mentioned earlier that for octa we make groups of 3 and for hexa we make groups of 4. So since we want to find an octa, we make groups of 3 and we start before the decimal place, we move from right to left. So 0, 0, 0, we write that. Then 1, 0, 1, we write that. Then 0, 0, 1, we write that here. Then we get 0, 1, 0, we write that right here. Then similarly for after the decimal place, we move from left to right. So this becomes 1, 1, 0. Then 0, 1, 0, 0, we write that. Then 1, 1, we write that 1, 1 here. But since we want to make a group of 3, so we add 0 after that. Now we convert this number to the octa number, this binary number to octa. So according to the table, the octa number for 010 binary number is 2. Similarly, 4 in octa, 5 in octa, 0 in octa, 6 in octa, 4 in octa, and once again 6 in octa. Okay, now let's cover some theory. The ASCII, also called the American Standard Code for Information Interchange, is a character encoding scheme based on English alphabets. While ISCII is the Indian script code for information interchange. It is capable of coding 256 characters and it is an 8-bit code, while the ASCII is a 128-bit code or 2 to the power 7. This is an important difference, please note that. Now, after the ASCII and ISCII, we all felt that these weren't compatible with all the devices throughout the world. It could only work in some specific devices. And to bridge that gap, Unicode came in. And it provided a unique number for every character. And it didn't matter where in the planet we were, what the platform was, what the program was, what the language was. So this actually helped in programming and making things extremely fast and efficient. We come to the end of this section, and I really want to emphasize that this chapter is all about practice. The more you practice, the better conceptual clarity you will get and the quicker you will be in solving such problems. So I have brought some practice questions for you. Please try them on your own and let me know their answers in the comment section below. And so these are some of the few questions. We covered all these changes like converting converting base 10 decimal numbers in the form understood by the computer. So the form understood by the computer is nothing but binary, as I mentioned earlier in the video. So we convert base 10 to base 2. For this, try solving all these problems on your own. If you're unable to do them, I would advise to go back to the video where we show the conversions from decimal to binary. Check the examples out and try solving the same questions by the method shown in the video before. Next is conversion from the decimal to octal. This is also what we covered. Then, uh, then these are of different bases, and we want to convert them all into decimals. Then is the binary representation. So this is how you would proceed. And there is one more. There are some more few questions which you can practice. So first is converting from decimals to hexadecimal. Next is expressing the following hexadecimal numbers into decimal numbers. Then converting binary to octa and hexa. Writing binary equivalent from octal numbers. And try solving these conversions on your own. And once again, please put them down in the comment section below. Thank you so much, everyone. I hope you understood and enjoyed this video. Please go back to the video if you feel that there's confusion at any part and rewatch it once again. As I mentioned earlier, this chapter is all about practice, and the more you practice, the better you get. Also, do check out our website in the link in the bio below for more such resources, practice material, tutorials, etc. Thank you so